in our department and teaches numerous meteorology courses in our growing meteorology program. And he's going to has a wide range of interests in different aspects of hurricane development and hurricane effects on society and people. And today he's going to talk about Florida hurricanes in a changing climate.
Thank you, Mike. This is going to be, I'm glad he used the word wide-ranging. First, this room is notorious for absorbing sound. Can the people in back, can you hear me okay? Am I loud enough? Okay, good. So I'm going to start with maybe going a little bit afield from Florida. This picture is not a picture of a Florida hurricane. This is probably in Long Island at the aftermath of Hurricane Sandy. And there are a couple of things but there's a reason why I'm bringing this up. What I like about it, well, not what I like, but what makes it a dramatic picture is the way this guy's shoulders are kind of stooped, and he's not a happy camper. And these buildings are damaged, but you notice the windows aren't blown in. The ground floors are washed out. These buildings were destroyed by moving water. And that was the story of Sandy. Now, I really debated about showing this slide, but I think it makes a point in my talk. Those of you who are on the faculty probably received a postcard with this image on it 8 months, 10 months ago, something like that. A right-wing organization, not the Heritage Foundation, the Heartland Institute. And I actually know some of the people in the Heartland Institute, establishing my credentials as a right-wing crank. And there are three threads of thought in this picture. One is Al Gore saying Hurricane Sandy is a disturbing sign of things to come. Our president saying you can't attribute any particular weather event to global warming. Two serious people with a legitimate difference of opinion. And then you have the people who put up the billboard, who are saying there is a difference of opinion. Can't those climate radicals get their stories straight? And so, and this is something we need to think about, because what I'm going to argue is that allowing the sort of poisonous atmosphere in American politics in the 21st century to come into what is a legitimate scientific debate is really doing everyone a disservice. So I'm going to go on from there. Since I'm talking about hurricanes in Florida, I call this the paranoids plot. Well, let me explain what's in here, and then I'll come back to why it's the paranoids plot. This is taken from the HERDAT file that our friends out on 117th maintain. It's a digital record of every hurricane that we know about going back to the 1850s. The records are pretty sketchy over 100 years ago, but nonetheless, it's a record of what we know. The little triangles connected by dots, the triangles are the position of a hurricane at 6-hour intervals. The red circles represent South Florida landfalls. You can barely see them because they're blocked out by the blue squares, which indicate the position where the hurricane reached its greatest intensity. And what I did was I've got a little box that includes it goes out to the Keys. It includes everything in South Florida, Southwest Florida, Southeast Florida, the tip of the peninsula. And what this shows is every hurricane that at some point in its life cycle, between 1900 and 2004, went through that box. South Florida is the most vulnerable part of the U.S. coastline in terms of hurricanes. What you notice about these hurricanes, they generally move southeast or southwest, southeast to northwest, south-southwest or south to north, and then northeast. So hurricanes come at us over the western end of Cuba, through the Yucatan Channel, sometimes even, well, actually not so much over the Yucatan Peninsula, and also north of the islands, north of Hispaniola and Cuba, Puerto Rico. And we don't get hit so much from the Central Caribbean. But this just gives you an idea of where the threat comes from. And the reason I call it the paranoid's plot is, you know, they are out to get us, right? And so let's talk about global warming. Al Gore, the Interdepartmental Commission on Climate Change, there is an international consensus about global warming. It has some of the shortcomings of big science, but it's also almost entirely composed of very serious people who are trying to do the best that they can. It's also composed of ambitious people. And being on the IPCC is a good thing to do for your career. And there is some tendency to look for one kind of result rather than another. So let's go over the evidence. I mean, people in this room, I don't need to spend a lot of time on this. The world's getting warmer. It's warmed by 0.7 or 0.8 of a degree Celsius since 1900. But you want to look at this warming trend a little bit more carefully. In the 19th century and the early 20th century, the temperatures were more or less constant, apart from oscillations up and down. What you see here, the black curve is the yearly values. And reconstructing this stuff is not easy, because what you have to use is standard exposures of ordinary mercury or alcohol and glass thermometers for the most part, until you get to the late part of the record. The stations move, the exposures change a little bit, cities build up around stations that you've used for a long time, and they're contaminated by urban heat islands. Stations get discontinued, stations get established, and there's a very, very careful program of tracking the station as long as it gives good data, looking at the stations around it, and making trend lines that actually reflect the changes where the data aren't contaminated by some sort of instrument issue. There are people who spend a huge amount of time doing this. But it is, to some extent, a subjective process. The Koch brothers, the oil service tycoons, whose politics are, shall we say, somewhat more conservative than mine, funded a reputable non-meteorologist to go back through the same data and try to do the same kind of reconstruction in an effort to show that those grant-hungry scientists were perpetuating a fraud on the American people. And what happened was he hired people who were good scientists with a lot of integrity, and they got the same sort of answer. I mean, different in detail maybe, but basically the same answer. So this is a good record of what's happening with the planet's temperature. There are several organizations that maintain slightly different records. People are doing what they should be doing, and they're doing it honestly. But what you see is, if the record could be extended back into the past, the world was getting colder up until 1900. Think about the picture of Washington crossing the Delaware. The Delaware was frozen. There were big chunks of ice floating in it. People used to ice skate on the Hudson regularly in the wintertime. The world was significantly colder in the 19th century than it is now, and it was getting colder gradually. And it began to warm seriously a little bit after 1900. It warmed until about 1940, then it cooled until roughly 1979, 1980, and began to warm again. Since, well, depending on what year you pick, sometime in the late 90s, sometime around 2000, the world hasn't been getting much warmer. if you are a skeptic, you say, see, it's not getting warmer. Well, there's more to the story. Sea level rise. The ocean level rises 2-3 millimeters a year right now. Seems to be accelerating just a little bit. I would argue, and then I was going to show, but I didn't connect it up, there's a marvelous animation that you can find from NASA of the retreat of ice in the Arctic Ocean. Basically, in the Arctic, not so much in the Antarctic, but in the Arctic, sea ice, the minimum sea ice, is more of a minimum each successive year. Not always going down, but mostly retreating. What happens when sea ice retreats is ocean water is dark compared to ice, which is white, and a thing people don't realize is as much solar heating comes in right around the summer solstice in high latitudes as does in the tropics. It doesn't keep doing that very long. There's only like about 6 weeks when you've got a lot of sunlight falling on the ground in the Arctic. The reason why there's so much solar heating is, yeah, the sun's low in the sky. At the North Pole, it's only 23.5 degrees above the horizon, but it never sets. And so when the Arctic is covered with ice, that sunlight falls on the ice, reflects out in space, and the Arctic doesn't get warmer. As the ice melts, ice albedo feedback is what meteorologists call it, or climatologists, that kicks in. And what I would argue is what's making the planet get warmer is that we're putting greenhouse gases into the atmosphere that causes the ice to retreat, and the ice albedo feedback amplifies the effect, and that this whole process is kind of unstable. If you push it a little bit, it might go one way, it might go the other. But what we're doing with putting greenhouse gases in is we're pushing it in one direction all the time. And things like ice extent, sea level rise are what the engineers would call low-pass filters that track the actual underlying trend more, for example, than temperature. Now, sea level doesn't always rise in every year. If you have a big deluge in Australia, there's a whole bunch of water standing on the ground around Alice Springs, and it's not in the ocean. And so sea level rise might slow or might even stop. On the other hand, widespread droughts make sea level rise apparently accelerate. But it's a low-pass filter in the sense that we get a constant trend. And it seems to be an accelerating trend. Not accelerating that much, but accelerating. Now, time series algorithms are kind of a hobby with me. And I came across a paper by Wu et al. In Climate Dynamics, Intrinsic Modal Functions. And it's a nice way of filtering a trend out of an oscillation. They ran the same data, the global climate data, through their algorithm. And what this is the rate of change of temperature, smoothed in an orderly way, but it's kind of an unconventional way of doing it. And what we see is a trend that becomes more uncertain near the end. That's the way time series are. And superimposed on it is a sinusoidal oscillation in the rate. And so, wait a minute. You know, the world was getting warmer up until about 1940, then it stayed the same or got a little cooler, and then it got much warmer in the 70s and 80s, starting in the late 70s or early 80s, and now it's starting to go back down. So what we've got, a reasonable argument to make, is we've got a warming trend that's at least initiated by us humans digging up coal and burning it, pumping oil out of the ground and burning it, and fracking the Midwest to get methane out of the ground and burning it. So, and why should we be surprised that there's a natural oscillation superimposed on it? It makes it a little difficult to sort out the trends, but we know that the climate skeptics will say it's all natural cycles. Well, what we're saying is, yeah, they're natural cycles, but there's a trend underneath it. And you guys believe in natural cycles when it's convenient, and you disbelieve in it when it's not. A thing that happens in the global warming debate, which I've watched for a long time, is if there's suddenly a string of really warm years, people who are alarmed about climate say, oh, see, the world's getting warmer. And the skeptics say, don't be a wiggle watcher. And then what has happened in the last few years when it's not getting warmer, the skeptics say, see, it's not getting warmer. And the alarmists say, don't be a wiggle watcher. And the moral of the story is, let's look at it rationally. And just go back and forth. This is the rate of change, and this is the actual time series. But you can see that they relate to each other, which makes sense. I mean, this curve is just this curve run through an algorithm that takes out the noise. Okay. Now, why should we find AGW credible? I do not use the word believe. We're not having a religious discussion. We're not, it's not whether you believe or not, it's whether you find the evidence convincing. The actual observed warming, the corresponding increase in CO2, melting of ice and rising sea level, which filter out the wiggles, well-established physical basis, which I'm not going to go into. A lot of the arguments that you hear on both sides of the debate don't really understand the physical basis. That's something we could maybe profitably explore at another time. Commercial message for the global climate change course I'm going to be teaching next spring. But the physical basis is well established in the sense that you can explain it, point to examples elsewhere besides the Earth, and it's also the numerical models have given us consistent results for 40 years. The models have gotten more sophisticated, more elaborate, and the results have been consistent and consistent with observations. Now, they don't forecast the amplitude and phase of that cycle. They don't do El Nino very well, but they do pretty well in terms of forecasting the long-term trend. And the thing that makes things tricky is the natural fluctuations around the mean. There are counter-arguments. There's a thing called the Dansgaard-Oeschger cycle that we know about from records of glacial stuff in the North Atlantic, where you have gradual cooling, such as happened in the 19th century, followed by relatively abrupt warmings. People correlate that with all the Germanic hordes getting their act together and invading Rome, that one of those cycles happened at just the right time. I'm a little skeptical about that, but it's something that's well known. It's possible that the natural cycles people have more realistic stuff, more believable stuff to say. See, I always use believe. More credible stuff to say than we're giving them credit for right now. So that's a possible counter-argument. There's a common intellectual heritage in the models. Everybody that writes models took dynamic meteorology from more or less the same textbook. And they're all the ad hominem self-serving economic arguments. Climate modelers want to alarm everybody so they can write proposals to the NSF and OGP and get funded. There are probably some people like that, but not the main thing that's going on. So I want to talk a little bit about empiricism. Sir Francis Bacon, the founder of modern empirical thought, he talked about four idols. And I'm taking liberties with Sir Francis here. They're the idols of the tribe, the foundation of human nature, how we learn from experience, how we don't learn from experience, how things that happen on time scales longer than our lifetimes, our natural lifetime time scales, tend to be things that we don't make credible. Idols of the self, individual experience and prejudice, idols of the marketplace, commerce and career advancement, and idols of the theater, celebrity. The shadows of all of these idols fall on the debate. People are human. Why should we expect that the people involved in this debate don't have the same motivations that human beings have always had? Actually, I would argue, we scientists are a lot more noble than the average running person, but we're not perfect. And of course this is here. Of course the shadows of Bacon's idols fall on the debate. But just because some of the people who worry about global warming don't have pure hearts, should we disbelieve the scientific consensus? I don't think so. Okay. So one of the things we need to avoid is confirmation bias. Psychologists talk about it all the time. You already have an idea, something happens that fits in with it. Ah, yes, I must be right. Mismatch between the 100-year time scale of global warming and human events in our lives. You know, we have a short time scale in our lives, sort of 5 to 7 years, the 7-year itch of comedy movies, the statute of limitations for most felonies other than murder. There's kind of that, you know, not a decade and not 2 or 3 years. Then there's a 70-year time scale in technological revolutions, a few decades time scale in political changes in a country. So we haven't really thought about global warming in terms of those time scales. It may happen slowly enough that we can adapt to it. Not something I'd want to bet civilization on, but it's conceivable. On the other hand, it's possible that we're going to go over a tipping point, and for example, instead of rising millimeters a year, the ocean would rise centimeters a year, or multiple centimeters a year, which would be very difficult to adapt to. And it is the trenches that are going to get us. It's potentially the greatest catastrophe in human history, and we really need to think rigorously and objectively. We need to not let Bacon's idols block our thought. And to some extent, although it's hard not to, we need to not demonize people we disagree with. Although I have to admit, sometimes it's really easy. This is an example. Many of you got a copy of this book after you got the postcard that I showed you. I have a whole collection of these books. Every summer, my family and I go to Marco Island for a week. And one week, my plan was to sit around and drink mojitos and read those books. After you've read 2 or 3 of them, they're all the same. So what does all this have to do with Florida hurricanes? Kind of provides the context. Okay, hurricanes. Wind in a hurricane blows around in a circle. In my hurricanes class, I say to everybody, hurricanes are round. If you don't learn anything else, learn that. Wind blows around in a circle. In addition to that, the air spirals in at the surface, rises mostly in the eye wall, the ring of clouds that surround the eye that you see here in green. It rises, goes up to the tropopause, the boundary between the troposphere and the stratosphere, and flows out just below the tropopause. Kerry Emanuel, a meteorology professor at MIT, and don't tell anybody I said this, but the smartest man in the field, worked out the energetics of a hurricane. It gains energy from the sea as heat, mostly stored in water vapor, latent heat. The water vapor and the warm air converges to the eye wall. As the air rises in the eye wall, water condenses into liquid water. The latent heat appears as sensible heat and actual temperature rise. The air rises up to the tropopause level and flows out at a colder temperature. The difference between the heat going in and the heat going out is the energy that's available to do work. Carnot engine, classical heat engine from thermodynamics. I had thought about this problem for, 8 or 9 years before I got Kerry's paper to review. And it was one of those experiences in science that you have when you go, there was a folk song that I heard once when I was driving around on Saturday afternoon on NPR that said, life is hard, especially when you're dumb. You work and work for years and inspiration never comes. That was the way I felt when I got his paper to review. But this is the basic energetics. And what it does is it gives you something that we call MPI, maximum potential intensity. In my hurricanes class, I say hurricanes are like students. Most of them don't live up to their potential. That usually gets a laugh, but not always. But the MPI is proportional to the temperature at the bottom, Tn, minus the outflow temperature, divided by the outflow temperature. Just exactly like a steam engine. The same cycle that makes electricity at Turkey Point or in a coal-fired power plant, roughly the same cycle that makes the engine in your car make energy. But we can calculate the MPI if we know how warm the ocean is and how cold the air at the outflow level 15 kilometers up in the tropical atmosphere is. The colder the outflow, the warmer the ocean, the more energy available to do work. Well, after Terry's paper was published, Mark DiMaria and John Kaplan, who worked with me at the Hurricane Research Division, said, let's try this out. So they took maps of sea surface temperature and intensities of hurricanes, and they found the strongest hurricane for each sea surface temperature, every half degree or so. And that's what gives us the black curve. The blue curves are a manual for a minus 70 degrees Celsius outflow, minus 75 and minus 80. Climatologically, the tropopause, the boundary between the troposphere and the stratosphere, is higher when the sea is warmer. And so it's colder. So the fact that the DiMaria and Kaplan curve crosses the Emmanuel curve adds credibility. So we really think that this thermodynamic argument gives us a measure of how strong a hurricane can be, the MPI, maximum potential intensity. And so, obvious conclusion, the ocean gets warmer, hurricanes get stronger. But there's more to the story. Just to show that the maximum wind is related to the pressure in the surroundings minus the central pressure, roughly proportional to the square root of the pressure difference. So if you think about it for a minute, an extra millibar pressure drop in a really strong hurricane produces less of an increment in wind speed than a millibar pressure drop in a tropical storm. But basically, the lower the pressure, the stronger the wind, the warmer the ocean, the lower the pressure. But it doesn't work equally well as the pressures get very low. Pressures in the centers of hurricanes can vary from, if it's a hurricane, from 980, 985 millibars down to below 900 millibars in a Category 5 hurricane. The record was, I think, Hurricane Wilma, I don't remember. Somebody?
882.
882, thank you. I blocked that out. I measured the previous record. And
888.
but trashing New Orleans was bad enough, but destroying my record, I really, I'm still mad about that. Okay, so hurricane intensity. MPI, if you go out in the middle of the tropical ocean this time of year, somewhere out south of Bermuda, and measure the sea surface temperature, launch a radiosonde, measure the tropopause temperature, you can get a Category 5 hurricane thermodynamically, just almost anywhere. And Category 5 hurricanes are really, really rare. Most hurricanes don't reach their MPI. You hear the forecasters talk about shear. What it means is the upper level westerlies are down over the tropical easterlies, so the wind changes as a function of height around the hurricane, and that makes it harder to get to its MPI. It's like you went down to Turkey Point, knocked a few blades out of the turbine, which would land you in jail very quickly. And the hurricanes also mix cold water up from below. If they're moving slowly, that damps their intensity. They form new eye walls around the original small eye wall, and the new eye wall is generally weaker, but it strangles the original eye wall. So they go through cyclic intensity changes, and they also simply run out of ocean, or warm ocean. They recurve into high latitudes, move over cold sea, they run on shore before they get to their MPIs. So again, most hurricanes don't get to their MPIs, but the ones that do are the ones where we would expect to see a global warming signal. The strongest hurricanes will, it's almost metaphysically certain that on a warmer globe, the strongest hurricanes are going to get stronger, unless something happens to keep them from getting to their MPI. So let's look at the 22 strongest Atlantic hurricanes since 1974. Somebody who's taken the hurricane class, why did I pick 1974?
Because that was the start of the cooling, the quiet period.
No.
Satellite measurements?
Yes, exactly. That was when the geostationary satellites went up. So nothing could happen in the Atlantic that we wouldn't know about. Now there's been reconnaissance since 1944, but the reconnaissance airplanes can't be everywhere. But once we had satellite measurements, so what you see is, again, same diagram that we saw before. The triangles are 6-hourly positions. The blue squares are where the hurricane reached its greatest intensity, which is 130 knots or 67 meters a second. The 22 storms all had maximum winds stronger than that. And the red circles are where they made U.S. landfall. And what you see is there's sort of three groups. There's the Caribbean, and even down a little bit east of the islands. There's out in the Atlantic, and a few in the Gulf. These three are from 2004 or from 2005. It's Rita, Katrina, and no, not Wilma. Wilma's down here. No, not Charlie. I'm trying. It doesn't matter.
Right.
And this is the occurrence. And what we see is, starting in 1995, we had a lot more of these. When I first began flying out in the Atlantic, here in the Atlantic, the conventional wisdom was that the Western Caribbean was Death Valley for hurricanes. There was too much shear. Even though the ocean was warm, and the ocean's warm down to more than 100 meters. So a hurricane in the Western Caribbean, if it isn't limited by shear, that's a wonderful place to be a hurricane. It's a wonderful place to be a Category 5 hurricane. But until 1995, there was too much shear. The one exception was Hurricane Allen, which formed way out to the east, came through the islands, romped its way the whole length of the Caribbean, reached maximum intensity going through, going through the Yucatan Channel, and eventually made landfall on the Mexican coast. And it was in August, early August, and we said, this can't be. I mean, hurricanes don't form this early, they don't get this intense. Because all of the people I flew with, our experience was the 60s and the 70s, and suddenly it was 1980, and Hurricane Allen came through. And then, not much along those lines happened. Hurricane Hugo down in the east of the islands gave us a very interesting afternoon 25 years ago, 2 or 3 days from now. But most of the time, Category 5 hurricanes were rare until 1995. And a couple of things you want to recognize about this. You do see some hurricanes out in the open Atlantic, mostly from early in the period, and most of these hurricanes made landfall. About a third of them made landfall as major hurricanes with winds more than 100 knots. But on the average, it was more than 3 days after maximum intensity, and they were 2 or 3 Simpson-Safford categories weaker by the time they made U.S. landfall. So for the most part, the hurricanes that strike the U.S. may have been Category 5 hurricanes, but they're not when they get to us. The ones where the generalization fails, Hurricane Andrew is a really good example. Hurricane Katrina, which was the most deadly hurricane since the 1928 hurricane that killed all those people in south of Lake Okeechobee, Hurricane Katrina was nominally a Category 2, but it really was probably weaker than that almost everywhere. It was not wind that caused all the deaths in Katrina. The people drowned. So here's the Florida big ones. 1900 to 1995, I think there are 11 hurricanes. And this is a real rogues gallery. The Keys hurricane of 06 and 09 disrupted the building of Henry Flagler's Railroad. The Havana-Tampa hurricane of 1944. If that happened today, it would be a huge disaster. People hardly even remember it. You see Hurricane King of 1950, which was a little tiny, intense hurricane that came right up Biscayne Bay. Again, we don't remember that, but again, it would be a huge disaster. The Lake Okeechobee hurricane of 1928 that killed 2,500 people in South Florida, and there were a lot fewer people there now than there are now. Than there are now. Andrew, the Keys 1935 storm that ended Henry Flagler's Railroad to Key West for good. Betsy in 1965, which made 2 loops, came through Miami and headed for New Orleans, where it was the design hurricane for the levees that failed in Katrina. Then we have Katrina, which also, these two tracks here are Katrina and Betsy. The other track in the Gulf is the 1926 hurricane, which if it happened today would cost more than $100 billion with a B dollars. So we're really vulnerable, and these are the big ones because, hey, I teach about them in my class. I mean, that's the criteria. So now let's look at 2004 and 2005. Same diagram. This is 2 years, 6 hurricanes. In 2004, we had basically Francis and Jean were the ones that made a lot of impact. Charlie that struck the southeastern coast, and then Ivan, and then in 2005, Dennis, Rita, and Wilma. There's another one. What am I missing? Oh, Katrina, of course. Yeah, I had to put that up there because they were too close together. They all crossed right in here, almost all of them. Bad place to be in your canoe that summer. And they all crossed, the Florida loop current comes up, the Florida current, the loop current comes up through here, makes a hairpin turn up in the Gulf with very warm water, very deep layer of warm water. And these Category 5 hurricanes that formed here formed either on the very deep layer of warm water in the Western Caribbean, or over the loop current, or over the Gulf Stream. And so the ocean plays a big role in our neighborhood, and it's not just the surface temperature of the ocean, but the thermal structure at depth. And I'm hoping that the reviewers of the NSF proposal I'm writing with Nick Shea agree on that, and we get funded. So let's look at landfalls by state. I mean, I've kind of drifted away from Florida to some extent. Florida is hurricane central. Florida is divided into northwest, southwest, southeast, and northeast. And what you see is lots and lots of landfalls in Florida. Then as you go north, there's another peak in the Carolinas where the coastline juts out to the east. Because the storms are mostly going north at that point, they hit the sort of northeast southwest coast south of the Virginia, south of the Carolina Capes. And then again in New York, Connecticut, Rhode Island, Massachusetts, and even Maine, again the coastline goes out to the east, Long Island. And so if the coastline's perpendicular to the average track, you get hit a lot. Then as we look to the west of us, Mississippi and Alabama don't get hit very often because they don't have a whole lot of coastline. And then Texas has a long coastline, so the density of landfalls is less, even though there are a fair number of them. And the Texas coast is divided into North Texas, Central Texas, and South Texas. But the point is that landfall is kind of constant until you get to northeast Florida, then it's low until you get to New York, and then a little bit higher, I mean, in New England. And New England is not invulnerable. If we look at the number of landfalls, U.S. landfalls, now, wait, let me go back. The gray on these graphs is non-major hurricanes. There are no minor hurricanes, so these are the non-major hurricanes. So those are hurricanes between the threshold of hurricane intensity, 65 knots, and roughly 100 knots. And then the major hurricanes are the ones with winds stronger than 100 knots. Major hurricanes do 80 to 85%, depending on what period you look at, of the U.S. damage. So what you worry about is the major hurricanes. And what you see is the Florida and Gulf Coast gets most of them. The Carolinas get a lot of landfalls, but relatively few majors. And then as you go into New England, they still get some major hurricanes, but their total incidence is a lot less. So here's time, same data, but expressed as a function of time. And what you see is a decrease in the number of landfalls with time, not statistically significant. And you do any of the tests, take into account that they're not normally distributed, you do the test right, yeah, it's going down, but it could just, by chance, you're looking at a 50-50 chance of that much of a decline. But what produces the decline is you look at the time from 1970 through 1995. Fewer landfalls there, lots of landfalls since 1995. And big peaks in the landfalls. I mean, 2004 and 2005 were comparable with 1933 and some of the other really big years. The one exception is 1985, the year when I didn't sleep in August and September. And but the point is that what's producing the downward trend is an anomalous 30-year or 25-year period from 1970 to 1995. North Atlantic tropical cyclones, this is a count of total tropical cyclones. Well, it's actually hurricane, well, it's total tropical cyclones, a little bit different. The dark blue is major hurricanes. That is, they were major hurricanes at least one time during their life cycle. The gray is non-major hurricanes, and the lighter blue is tropical storms. And what you see here is it looks like there's kind of a wave, and the bottom of the wave sort of lines up with that minimum in damage. I mean, the minimum in landfalls. And superimposed on the wave is an increase. Well, why would the number of hurricanes be increasing and the number of landfalls would remain sensibly constant? One possibility is there really are more hurricanes and they're staying out to sea. The other, somewhat more likely possibility is there was always a lot of hurricanes, but we didn't know about a lot of them. I tell my students in hurricanes class, the way we know about hurricanes from before 1944 is ship logs. You drove your clipper ship into a hurricane, the ship log didn't end up back at the hydrographic office, it ended up down with the hagfish at the bottom of the ocean. So, and it's also true that after about 1840, officers on ships knew that hurricanes were circular storms, and they knew how to avoid making inadvertent low-level penetrations. So the argument that I accept is the increase in numbers since 1881, which was the old beginning of the HERDAT file, is pretty much a data artifact. So let's look at normalized hurricane damage. Roger Pilkey at University of Colorado and Chris Lancy, who works here at the Hurricane Center, he's the Science and Operations Office, corrected historical damage for inflation, which is the obvious one, population of the county where the damage occurred, which is, I'm starting to think has some statistical problems, and greater personal wealth. And so it tries to answer what would historical hurricanes cost with 2005 population and development. That was the year that they ended their study. And the average damage over that period is $11 billion a year based on the 1900 to 2006 data, and then with 2007 and 2008 added on to the end and kind of corrected in an ad hoc way because it was only a couple of years. So let's look. Here's inflation-adjusted damage, doubles every 15 years. Because there's more people on the coast, they own more stuff. Normalized damage stays steady at about $11 billion a year. And I've labeled, famous hurricanes. And again, there's kind of a lull between Agnes in 1971 and Charlie Francis Jean, etc., with the exception of Andrew. So you see a lot of big spikes back here, just one here, and then this time here. And this is the lull, 1970 to 1995. And again, we don't see a dramatic increase if we look at deaths, and there's no way to correct deaths. I mean, somebody dying is somebody dying. But what you see is that the number of deaths decreases by 50% every 25 years. And there's a big respite in people being killed by hurricanes between Agnes in 1971 and Katrina in 2005. And you know, let's include 2004, where a fair number of people died, but you know, not a spectacular loss of life. So the damage statistics are consistent with the damage and mortality statistics, and basically the reason we're seeing the reduction in deaths is because we do a pretty good job of forecasting. Most people who die in hurricanes drown. If you're not where the storm surge can get you, and not where a flash flood from the torrential rains can get you, your odds of dying go way down. You still can get skewered by a board blown off your neighbor's house, but it's much less likely. So year-to-year variations. Apparent increase due to data issues. El Nino. When El Nino is in, there's a lot more shear over the Atlantic, and you have fewer hurricanes. The Atlantic multidecadal oscillation, which is sort of a biblical oscillation in the number of hurricanes, snowfall in the Alps, river runoff in North America. Basically, they're warm ocean currents during the warm phase. Shear over the Atlantic is less, and we have a lot of hurricanes. During the cool phase, we have stronger shear. The Atlantic Ocean is cooler, but the dominant thing is the shear and fewer hurricanes. And then global warming, which we've talked about, stronger MPI, but probably more shear too. And then there's chance. So if we look at El Nino, the blue are the La Ninas, when the water off South America is cooler than normal. It's normally cool, but it's cooler than normal. The reds are the El Ninos when it's warmer, and the pressure difference between Tahiti and Darwin tracks those temperature differences, and we have a record of that going back to the 1870s. The Bureau of Meteorology in Australia maintains that, because El Nino also controls rainfall in Australia. During El Nino years, they have whopping droughts. So we have this time series. If we look at hurricanes during an El Nino, let's go forward. This is an El Nino year. Not a whole lot of hurricanes. This is a La Nina year, which, you know, not a fair example, I admit. 2005, most active year on record. Lots and lots of hurricanes. So El Nino gives us, it adds noise to the time series.
What was the La Nina year again?
1982. We were trying to find a hurricane to fly all year. It was the mirror image of 85. I slept a lot in the summer of 1982. And so the Atlantic multidecadal oscillation is an episodic warming of the Atlantic. The tropical Atlantic, it's kind of shaped like a backward C. The water right near the US coast gets a little bit cooler. Again, we have records of that because the chief engineers on steamships had thermometers, and the steam engines worked just like the Emmanuel cycle. The colder the ocean and the hotter the boilers, the more horsepower you had to drive the ship. So they measured the water, intake water in the temperature of the intake water, and they entered it in the logbooks, and we've got the logbooks. So we can reconstruct the AMO, again, back to the 1870s, and here's the cool phase in the early 20th century, warm phase that extended for most of the middle of the century, in the present cool phase, that lines up with the minimum in hurricanes, and the minimum in U.S. damage, and the minimum in U.S. deaths. And just kind of go back and forth between those two diagrams. Well, let's go back.
What was the previous, between 1982 and 2005, what were you had an El Nino in 1982.
And 2005 was a La Nina.
Was a La Nina. And what were the El Nino years in?
Well, we can go back to I'd have to, you know, I don't remember a list of all the years, but I do have. If you're interested, remind me, and I have a list of famous El Nino years. There are people who, you know, that's their whole career. Okay. So model simulations, control climate. These are what we call downscaled global climate model simulations. So what they do, what the guys at the Geophysical Fluid Dynamics Lab do, is they run a global climate model with and without the high CO2 levels, doubled CO2 that we expect around 2100. and they do many replications. This is actually based upon the Community Modeling Intercomparison Project, which is global climate models from all over the world, different labs. And then that's used as boundary conditions for the models that we use to predict hurricanes on a day-to-day basis. And the models make hurricanes, and the hurricanes, this is what you get in the control climate, which is late 20th century. This is what you get. It's an 18 model ensemble with turn of the 22nd century, 2100. And what you see is more hurricanes and a shift of hurricanes into the North Atlantic. An alternative downscaling based on the same global climate model runs. And those global climate model runs, that's the absolutely kosher, approved by the IPCC, carefully vetted, thought through, look for errors, look for anomalies. They're making, it's a so say we all kind of series of climate runs. Same basic climate runs, different downscale. And this is worldwide, done by, again, Carey Emanuel. And this is the change in track density. Let's go back just a second. Number of hurricanes should decrease because of greater shear in the Atlantic. Strongest hurricanes can get stronger and rain more because the ocean's hotter and it's easier to evaporate water. The effect should be strongest in the Western Atlantic, neutral or weak in the Caribbean or Gulf, and we probably shouldn't be able to detect it yet. Then if we look at worldwide with Emanuel's downscaling, where he has a really clever little hurricane model that he can embed in the GCM. And it's really, the prediction models are sort of guys with ordinary intelligence like me working really hard to make a nice model. And Carey's model is a flash of genius and very possibly right. What that model predicts is this is the number, basically numbers, and the red means more. A lot more hurricanes in the Western Pacific off China and Japan's coast, recurving hurricanes in the Western Pacific, somewhat more hurricanes in the Atlantic off our coast, storms somewhat like Sandy, so Al Gore may have been right and President Obama may have been wrong in the second slide. And finally, an increase in activity in the southern Indian Ocean with a tiny increase in the Bay of Bengal. And that's a pretty specific set of forecasts. If we look at essentially a measure of intensity, most of the intensity increase is going to be in the southern Indian Ocean and in the tropical Pacific, both the eastern Pacific and the western Pacific, with a slight increase in the Atlantic, in both the Gulf and in the open Atlantic. Given the fact that these models are so different, there's a surprising amount of consistency here. I think that the numerical models are actually going to give us a pretty good idea of what to expect. Okay, I'm not going to do this. Suffice it to say, I'm not going to go through Pareto distributions or all the rest of this. I have 3 minutes left. But suffice it to say that if you look at hurricane seasons, the 10% of the most destructive hurricane seasons account for 2/3 of the damage. And what it is a nasty hurricane hitting a big city causes a lot of damage. A nasty hurricane hitting Kennedy County, Texas, where there are more cows than people, not so much. An ordinary hurricane hitting anywhere doesn't cause a whole lot of damage most of the time. But when you get the wrong hurricane in the wrong place at the wrong time, it's really bad news. Andrew, the 26 hurricane, the Galveston hurricane of 1900, et cetera, et cetera. And so the time series is characterized by these big hits, and it makes it really hard to tease out trends. So these are the hurricanes that cause the most destructive hurricanes of the most destructive seasons. And you see they look a lot like the Category 5s or the Florida big ones, except there are not a whole lot of hurricanes that come around the corner and hit us from the southwest that make this most destructive season list. So anyway, the Earth's getting warmer, primarily because of human activity, it's a hard argument to say anything else. There are counter arguments that we should at least listen to before we discard them, but they're not particularly credible, at least in terms of what we know now. Expect warmer oceans to cause more intense hurricanes, but we don't see credible signs of that yet. And we shouldn't, because the time series is naturally so noisy. Hurricane damage, nice statistical trend that shows the damage increasing. By the time we see that, we're already in deep doo-doo. We've got to base this on models and physical understanding. Detection is hard because of El Nino, the AMO, and just the fact that the really bad hurricanes come from a succession of factors all breaking wrong. And U.S. normalized damage is constant. Deaths have decreased because of better forecast. Numerical simulations predicted measurable effect sometime maybe in the middle of the present century. That may be optimistic. We may not actually be able to say that, but that's kind of what one might think. Fewer Florida hurricanes, perhaps, but more intense. That's not good news. And finally, I can't resist showing this slide. And thank you for your attention. Any questions? Yeah.
Is this year kind of anomaly because there's like nothing out there right now?
Yeah, and that's right. I mean, today actually turns out is the climatological peak of the season, and we have the remains of Gabrielle and a zombie cane, and Umberto, which is probably going to fade from view unless something very strange happens. And I mean, that's kind of the point, is the people who forecast hurricane activity on a seasonal basis were looking for a very active season, and there's more going on than what we understand. One possibility is, and I'm going on record saying this, but not very loud, is that we're actually at the point where we're shifting back into an inactive AMO, which is going to make it really hard to use hurricanes in advocacy for global warming mitigation. And we should kind of be careful about that. It's not a particularly good thing to use because there are these long lulls. That what we need to talk about in an advocacy role is droughts and deluges, wildfires in the West, and sea level rise. I think those are going to be the biggest challenges that humanity's going to face.
The prediction was accurate in terms of the number of named storms. We're up to H at this point, halfway through, and the prediction was that's exactly where we should be. It's just that none of them accept.
Yeah, but we also forecast ACE, accumulated cyclone energy, and we're going to end up with a third or a quarter of what we normally get. And the number of named storms, we're better at detecting them. We're naming things that we would have never known about 20 years ago, even in the satellite era. We've just gotten a lot better at that, and that's producing, and named storms. Major hurricanes making landfall is the thing you worry about. There's a clear bifurcation in U.S. damage between years where a major hurricane made landfall and none did. It's basically more than twice as much damage if you have at least one major hurricane landfall, and they account for 85% of the damage. So number of named storms isn't, yes, what you're saying is true, but it's not a particularly representative statistic. Okay.
So you showed the 2004-2005 hurricane paranoid map there.
Yeah.
There are about 8 hurricanes during the 2 years' time. Other than the fact that they all came through Florida, were there any common features across those 8 hurricanes?
Yeah, you can actually, if you look at the 2 years, you can make analogs between the hurricanes, and I forget what the exact relationships were, but I went through and I said, oh yeah, Katrina's like Francis. And what it was there was low shear over Florida and over the Gulf. There's always a lot of warm water with a very deep mixed layer. And the long wave trough that controls when the hurricanes recurve towards the north, the break in the ridge, the subtropical ridge, lined up so they either went over Florida and recurved in the Gulf, or recurved right into Florida coming out of the Caribbean. So it was a whole lot of stuff lining up. Jim Lusheen, who was the warning coordination meteorologist at the forecast office here, used to say hurricanes are like bananas, they come in bunches. And there are years like that where you have serial correlation in the tracks, sometimes for a pair of years, just bam, bam, bam in the same place. And we would really like to understand why that happens.
And I think in one of those years, your total number of hurricanes, cyclones, and all those storms together was the highest.
Yeah.
In 2005, I think something like about 28.
And and there was low shear and warm water, but there's been other years where there's low shear and warm water.
Was that a La
That's
Nina
now.
year, by the way? 2005?
Yeah.
That was a La Nina year, actually.
It was a La Nina year, but other La Nina years have been really active, but not like that. And 1985, right in the middle of the inactive AMO, was a hugely active year. And we'd love to know why that happened. And 1954 and 1955 were another real interesting pair of years. Yeah.
So what accounts for low shear conditions?
Basically, there is a pattern of wind where there's mid-latitude winds blow from the west, and the tropics the winds blow from the east, and the boundary between the two slopes towards the equator. And there's a pattern of wind during El Nino years where it swoops down over the eastern Pacific, comes up over North America, and then swoops back down over the tropical Atlantic. It's called the Pacific North America pattern. And when that's really well expressed, it's hard to make a major hurricane, except there's one little slot of low shear, and that's right where Andrew formed. Andrew hit us in an El Nino year. And so it's not always true that hurricanes have a bad time in El Nino years, but statistically it's not good to be a hurricane in an El Nino year. Anybody else?
In terms of damage, the impact of the hurricane, is the effect of sea level rise over the last century of a foot or so, is that going to impact the damage that, for instance, in Katrina or here, if we have the wet hurricane here?
It's probably very difficult to demonstrate with the present level of sea level rise. But, the number that I believe for 2100 is a meter of sea level rise by then, a meter since 1900. And, or maybe 80 centimeters, something like that. Now, there are credible estimates that take high estimates of ice melting in Antarctica and Greenland that are double that. But a meter is I tend to be conservative about these things, as you probably picked up. A meter is what some would have to convince me not to believe a meter. 50 centimeters or 2 meters or both take a hard convincing. A meter is going to be a real problem for us here, because the drainage canals are not going to work as well. We're going to have to pump a lot more, and it's just the storm surge is going to start a meter higher. And and in West Florida, it's going to be even worse, because they don't have a ridge along the coastline that we do. And it's difficult, again, what the president said in that second slide, it's difficult to attribute individual events to global warming. And let's suppose that Katrina and Irene were the beginning of a trend in New England. Looking at it from the perspective of 2050, we would look back and say that was the beginning of the trend. But while you're in it, before it becomes well marked, it's very difficult to define. And again, the statistically significant slope is not going to tell us anything.
I read somewhere that Hurricane Sandy wouldn't have flooded the subways in New York, 50 years ago, something like that.
There are people who've studied, there's a geology professor at the City College of New York, Nick Koch, who studies past New England hurricanes, and he looked at the hurricane of 1893, which is a great story, which we don't have time for. But he looked at that and said if that happened today, there'd be green water pouring into the subways in the Bronx and Queens. And yeah, I mean, every centimeter of sea level rise gives you that much less of a margin of error. But it was a bad storm even without sea level rise. And I mean, the one place where I would say that Sandy was connected to global warming is we really do think that there's going to be a shift to the east into the Atlantic of the centers of action. And that makes it easier to get a big storm that goes up the east coast. Not the intensity, and probably not the size, but the track of a big nasty storm. It might be easier to do now. But again, lost in the statistics, lost in the statistical uncertainty. And all I'm saying is, why should we worry about statistics? Let's try to understand. Yeah.
Do we still have rooms for improving our predictions of hurricanes in terms of getting them right? Because
Oh yeah, yeah.
I mean, if so, I mean, where are we, and where are the areas that we have to
Okay,
go?
the thing that, okay, the good story, well, it's two really good stories. One is if we know what the hurricane's going to do, we're much better at predicting storm surge. One of the reasons that so few people died after 1970 was we began using the very primitive slosh model to predict the extent of storm surge flooding and to evacuate the flooding zones. And even with relatively primitive track and intensity forecasting, that made a big difference. We knew where the water would come in, and we kind of developed a mindset that surge water is acid. If it touches you, you'll die. And so we evacuated people, maybe more than we should, but hey, they didn't die. So that's one big success. And building on that is the appearance of animated satellite pictures on TV, which made it a lot more real than, hey, the wind's blowing from a funny direction and the barometer's low.
Well, actually,
Okay. And then the other thing that we're doing very, very well, substantial improvement every year, is forecasting tracks. If you'd read the advisories on Umberto, they were forecasting that it would turn north and that it would go north for a couple of days and then turn towards the west. With Sandy, as it came up out of the Caribbean, they forecast that S turn to the east and then coming back and hitting New York. They did very well on that. The track forecast for Katrina was great and probably saved 10,000 lives. So track forecasting, big success. Intensity forecasting, we've made no progress in the time that I've been involved in this, which is since the early 1970s. And it's just a much, much more difficult problem. We have a new forecasting model, the WRF model. My former colleagues out at Virginia Key, and the guys at the GFDL lab, and university people throughout, Ping Zhu here, are all working with WRF to try to, you got to get everything right. And we're looking at the details of how you do the calculation. But what you really need is not only intensity, but the distribution of wind, because that controls the surge. We're going to start asking a lot more of surge forecasts, too. We don't want to evacuate people who don't need to leave because they clog the roads for the people. If they don't leave, they're going to die. So, and there's a lot to be done with social science, with understanding how people respond to warnings, with phrasing warnings in a more informative way, the timing. The whole enterprise is really demanding, and we've made a lot of progress, but there's a huge amount to do. And then another thing, we do this here, is designing buildings so that they'll be survivable. The wall of wind, all of that sort of thing. Yeah.
You mentioned about your new course coming up next semester. A lot of undergraduate and graduate students. Would you like to take this opportunity to
Well,
do a
we're going to be
marketing?